Good morning, everyone, and welcome to our last day of our We Meet at Digital Days 2022. My name is Eleni Stark, and I will moderate the presentation this morning. We are very pleased that you took the time to participate in our today's presentation. The topic will be EMI debugging of a low-power buck converter. The presentation will be held by our colleague Frank Puhane. He's our technical engineering. Before we start with the presentation itself, I would like to point out that you are going to be muted during the presentation. However, you can always ask us all your questions during the presentation via our chat function. You'll find the chat function in the control panel. The presentation will be about 30 to 35 minutes long, as my colleague told me already. There will be a Q&A session following the webinar, and we have 5 to 10 minutes in addition scheduled for this. If we are unable to answer all your questions within this time, we will answer them via email afterwards. If you still then have any other questions left, just mail us at exhibition@we-online.com. We will try to answer all questions promptly. At the end of the presentation, you'll be asked to participate in a feedback survey. We would be very pleased if you take your time to fill out the survey and help us to improve our event. You will receive the link to the presentation in the next few days. The recording will be available at our website shortly. Now we'll hand over to our speaker, Frank, and I wish you an exciting presentation.
Yeah, so good morning also from my side. It's very nice that you all took the time to participate on my presentation on the last day of the We Meet at Digital Days. So the topic, as Eleni already mentioned, is the EMI debugging of a low power buck converter. My name is Frank Puhane, and I'm the lead of technical engineering for iCap and iWis, so for our capacitors and resistors division. Yeah, what is the points I want to talk about in my presentation here about the topic. So first, I will go into what is my motivation about how we go into this topic. Then we have, of course, the first approach, so first design. For this, we did some EMI measurements, and of course, we do the root cause analysis about what was the problem, what is the problem, and how can we solve it. Then we go into detail about improvement of a design. So what can we do to get a feeling what are the next steps to finalize and to get our design running, and also to get to pass the test. Then of course we have a second approach or a second prototype where we then use all information and create a new design. Again, here EMI measurements to show, okay, this is what we did and what we found out helps to improve the design. And of course, in short conclusion about the points we are here talking about. So grab some coffee and hopefully you enjoy the presentation. So when we talk about power supply, power conversion, especially here now with a buck converter. So I choose a buck converter because nearly everywhere there is a buck converter. So we have a higher voltage, and we have to convert it into a lower voltage. Just as an example here from machinery, for example, with controls, industrial controls. So every inside control unit is a voltage regulator, and here especially also buck regulator. So in the end, it's everywhere. From the specification itself, we have 12 volt at the input. Output should be 5 volt, and output current around 1 amp. And as a switching frequency, we choose here from the converter 1 megahertz. As a short recap, so about EMC, EMI, What is, for example, EMC? So electromagnetic compatibility. There are two tests we are doing in the lab. It's the emission tests and also the immunity tests, especially from the emission, what we are concentrating today. So we will have some emission tests for our design. There is the conducted emission, where we have a shielded chamber and we measure the noise from the design, and also radiated, where we then measure with an antenna what is radiated from the design. So these are the two tests we are going in detail here. For immunity, there is also some conducted immunity and radiated immunity. Like what you see here is an ESD impulse. So this would be conducted, and radiated is when we place maybe some H field over an antenna. One word about a frequency range. So conducted is from typically from industry point of view 150 kilohertz up to 30 megahertz, and radiated from 30 megahertz up to 1, 2, 3, 4, 5. It depends on the switching frequency of the design. So it goes really in the higher frequency range. For us, it's really important that the EMC, EMI is considered from the beginning of the design. So it's really worth that you take your time to think about EMI or EMC. So you think about where you place your components, what current paths you have, what maybe also where could be some radiation. Of course, it will lead that it take more time, and more time is cost when you think about a design. But in the end, there will be some cross point where then in the final production, when the EMC is considered in advance, there will be of cost savings, because when you think about, you have a complete design, and then you go to the EMC test, and in the end you have to put in filters, combo chokes, grounding, housing, and so on. The rework costs will really dramatically increase, and so overall cost. So this is why it's really worth to take your time to think about the EMI. So coming back to our buck converter for this presentation, as you see, for this design, there was the IC chosen LT8610 from Analog Devices. What you see here on the left side is it's just copied from the data sheet, so the picture. So it's like really the minimum setup to build it up. There are also some design tools where there's some support to find the components. It's like here, it's from LT PowerCut, an Excel sheet, where we then get all the values and components what we want, or what we can use, and also get a feeling about stability and so on. So after we choose here our components, of course, we then go into the design phase. So the schematic was built up. This is also the schematic from the minimum setup. So we have our input capacitor here, output capacitor. So input side bulk, like a bulk capacitor, and here the input capacitor, output capacitor. Also placed some possibilities to change in the design. There is some power good, but I have to confess that it was not working, because it was the wrong schematic here, the wrong setup. And then our inductor here is a shield, also already a shielded one. So it's really a good choice for the inductor. When we had a look at the layout, hopefully a few of you think, "Oh my God, what has he done?" And of course, when we have a closer look into design, we see there are no wires, or no good connections to the ground. So also, especially from the filter components, we have some quite big current loop. Also, placement of the components is not the right one. And as I said, our ground concept. Especially looking at a magnetic loop antenna. So what I built up here with the C-in ground and the output ground is quite separated. The components, so the input capacitor C1 and C3 are really far away from the input pin. Also, the bootstrap capacitor is not really placed and connected in the right way with long traces to the component. And imaging we will place, I really tell something what I talk about later, but if we place a filter component, really the ground should be go over the filter and not connect directly from the input pin here, because otherwise it would lead to an galvanic coupling, and then of course there will be some issue with here. And again, the overall wires are not really there. So what we did, we go into the lab. So it's really, fortunately, we have in our headquarters in Wallenburg an EMC chamber, an EMC engineer who could help with these kind of measurements. So conducted emission, as I said in the beginning, from 150 kilohertz to 30 megahertz. From setup, we have some table. Here we have a wooden table. We have a conductive wall. So everything is connected to this wall. We have our device under test, our listen, and our EMI receiver. So this what you see here is some schematic overview. And here is the setup from our measurement. So voltage supply, our listen, it's from an 2-line V listen. We measured after the CISPA 32. And this was the cable. So we have quite long cables here. And also what is really important is the placement of the cable. So it depends how big is the distance between the cables and so on. It all change the measurement or influence the measurement. And we have some static load here. Then first measurement. So the setup is I show here. I know it's quite small, but that you see it's still the really the first setup. And of course, what I hope a lot of you expected, that there will be some issues, some noise. And we see we have no input filter. The bulk capacitor is like a aluminum electrolytic capacitors with 47 microfarad, 16 volt, high ESR, and ESL with around 19 nanohenry. So what we have at our switching frequency, so this is the fundamental frequency, we have around 100 dB microvolt as a noise. And of course, we are way over the limit lines here for quasi-peak and average. So this is, of course, an issue, and we have to figure out how we can solve it. Basically speaking, for the root cause, this is the picture on the right side here is an schematic about the input circuit. So we have some leads, some input cable, and then we have the input capacitor of the design. And depending on the voltage drop, what we have on the lines and also on the input capacitor, there is some voltage ripple and voltage drop, and this is what we measure then with our measurement equipment. And this is why a rule of thumb, or what is good to have, is that the ESR and the ESL of capacitor should be really small, so that the AC component of the signal of the energy doesn't have to be taken from the source. Especially ESL means that I can store energy fast and get the energy also fast out of the design. What we did then in advance is that we measured the conducted emission up to 1 gigahertz. We did this because we want to get a feeling how the design acts in higher frequency ranges. So you see up to 1 gigahertz here. This is the fundamental switching frequency, and we see that there will be from this measurement, we get a feeling, okay, there will be also some issue with the radiated emission. Of course, we then did the radiated emission from the principal setup. That is that you have also here a table. You have your device under tests, and yeah, of course, when you need a power supply or anything else, the cables go outside the chamber. That you really measure just your device. Sometimes you have your turntable, then you don't have to do the the turn of your design to figure out where the maximum radiation comes from and on which angle. But as you see in the right picture, we had some table with styro duo, and so we have to turn it by hand. We have here also some the static load. This is quite like a switch. You can move the slider to change the resistance, or here there's another possibility to have as a load. So this is static load, ohmic load. Yeah, so what I said in the beginning, our feeling was that we have some issue, and when we get a result of our design from radiated emission test, we see, okay, there is really a big issue, a broadband violation of the here especially quasi-peak measurement lines. Black is the vertical measurement, red the horizontal. You will see there's a difference on the orientation where we get the emission, so the emission height, the value. And so we also did, of course, some tests about what if we improve the design, if we can also improve the radiated emission. And but this was really quite hard. So radiated emission, where does it comes from? So from EMC point of view, buck converter is really critical on the input side. So there is some discontinuous current consumption due to the switching process. So this is the critical area. And the output, we have an LC filter, or already an LC filter. So the output side is often really more quiet because there is already a filter which integrates then the currents, but really the current from the loop from the switching is here the critical situation, and this is what we have to then solve in the design. So we have our here first improvement. So here you see also where we are in the circuit. So we change the input capacitor, so the bulk capacitor here. As I mentioned on the slides before, that there is some voltage drop over the input capacitor. So this was one thing we can try to improve. And really, when we change the technology, so we go from aluminum electrolytic to a polymer electrolytic polymer capacitor, same capacitance, voltage rating, you see that the ESR really goes down. It's really a huge improvement, and also the ESL goes down. So this leads when we concentrate on the fundamental switching frequency. It's still 1 megahertz, so we are now of around 70 dB microvolt. But yeah, in higher frequency there is some not really a reduction. Maybe we have some resonances or something else here. So, but when we just look at a switching frequency, we have an improvement, and when we change to a ceramic capacitor, so a multi-layer ceramic capacitor, also 47 microfarad, 16 volt, the ESL again really goes down here. This is because of the technology, and also ESL goes down because it's really short. The termination is really really compact, so we have not really long leads. This is why the ESL also goes down here. One word about MLCCs. So please keep in mind that when you apply voltage to the ceramic capacitors for class 2, there will be some drop of the capacitance. So you have an voltage dependent capacitance. It really depends on the size. So yeah, lower or smaller case sizes will lead to a higher capacitance drop. So this is what also I showed here. So going to compare 1206 and 1210, there's maybe half of the resulting capacitance. So please keep this in mind. And when you want to have a closer look at it, we have it in our online tool with Expert. You can compare the curves. And but what is missing and what we are try to measure is the impedance, so the voltage dependent impedance, and also show the ESR. So keep in mind also that the ESR change when I apply DC voltage. I change capacitor here, also I change the input capacitor, and I measure it also in a time domain. So here again, at the beginning was an aluminum electrolytic capacitors. We have an voltage ripple of around 519 millivolt, but the signal looks quite good compared to a polymer. As I said, same capacitance, same voltage rating. The peak to peak is 270 millivolts, so this was the improvement. But yeah, oscillation does not have to be bad in general. So from conducted EMC point of view, the polymer capacitor makes a good job. So it decreases the limits or the emission. But maybe the oscillation cause problem in radiated emission or in the end with the stability of the converter. From the stability, so in the event of an voltage transient, oscillation may occur at a switching controller, also the input. These oscillations are caused by a so-called negative input resistance in combination with an here LC circuit that is produced. Destabilization of the output regulation loop when the frequency spectrum of the negative impedance at the input overlaps, especially with the bandwidth of the control loop, then it can occur. And voltage overshoot in the event of a resonance, it's really can damaging the part and also some passive components, and in cause of other, and is also the cause of other EMC interference signals. So the risk posed by the negative impedance are greatest when the input voltage is lowest, and thus and also the input current then is the largest, is really large here. This is what I summarized here, and what you see in the graph is that that is negative input resistance really can occur. We did then some LT-SPICE simulation that we see, okay, what are the resonances here, and maybe what is the issue. So this is the simulation. So yeah, this is the input of the converter, and this is my input circuitry. Also here, I already did some filter here, and the components are as a real components. Like you see, there are the equivalent series resistance and so on. So these are the real components, and we see that when we have, of course, no one is doing it, but if we have no capacitor at the input, we have really high resonances, so it will cause then again instability. For the polymer and the MLCC capacitor, we have some resonances at around 10 kilohertz, sorry, 10 kilohertz. And with the when we use the aluminum capacitor, it's quite smooth, so it's also the input circuit is quite damp. So this is why it's really worth to stay here with the aluminum capacitors from the stability point of view, and we have to figure out how we get the EMC in the right value so that we go under the limit. For this, we had a look into the data sheet, and it's really nice that they already suggest some ultra low EMI filter setup. So with an like a pi filter with an coil, additional coil here. We build it up, so we have all components available with ceramic capacitors, ferrites, and also inductor with LQS, and we place it here in the green circle. So this is now our input filter, what we placed. And yeah, when you remember what I said in the beginning of the design, so I connect here directly ground, so the ground is not really going over the filter. So this will be also again an issue. So this is please keep this in mind, that this is important, that you really had a good ground concept here. Before we go into the measurements again, we did some trick, or we did some measurement in advance. So we measured with a current probe. So here you can measure then common mode and differential mode of the noise from differential mode and common mode. We see, okay, what is your emission? So the green line is not average, it's here the differential mode, and yellow is the common mode. So with the filter, we see, okay, it's really it's working. So the filter works. So in the beginning we was quite here with our emission, and now we are quite low. So filter will work. And then again, we did of course our measurements. So with the aluminum electrolytic, with the high ESR, with a good damping, we scratch the limit. So we are not really we are not under the limit, so this is not not the best solution. But when we are looking for the fundamental frequency, but when we look at higher frequency, it looks really good. But when we are not under the limit, we failed the test. We changed again the capacitor here with a lower ESR, and we see that we are really under the limit, but you see the same shape as before without the input filter, but with this we would be under the limit for conducted emission test. Regarding to the MLCC, so the ceramic capacitors, we are also under the limit, and here we have maybe a better shape of the harmonics here. But as I said before, really take care about the high capacitance MLCCs, because they lose capacitance, and then when there are some load transient, maybe it's too less capacitance to really have a stable design. Just to make here a recap about the radiated emission measurement. So here on the left side without input filter, so this was what we have in the beginning, and then we did a measurement with the input filter, and also with the combination with this polymer and MLCC, because it would lead to a good conducted. But still there are I would say it's broadband or a wideband violation of the limits. So still we cannot pass this test. So it will lead to us to have a second prototype and a second approach. So maybe you also remember from slide 11. So this was the input circuit with the voltage drop over the capacitor, input capacitor. So the ESR and ESL should be really small as possible. And here I did some thoughts, and we also used this then in the design. So still ceramic capacitor input side, so this 3C here. So really the input capacitor, which is at the IC pin. I go from 100 nanofarad to 22 microfarad. So this is quite a big increase. But you see here, when I compare it, the impedance is really lower, and also the ESR is really quite lower. Okay, we have when we had a look at the DC bias behavior, you see, wow, this is really a huge drop of the capacitance. But this is here, it's a really good thing, because when the capacitance drop, okay, the impedance goes up, but also the self-resonance frequency shifts to higher frequency. So still with this drop of capacitance, the part itself has better electrical parameters as the 100 nanofarad. To prove this, I did the measurement I compared the measurement from the design from a 22 microfarad capacitor with this 100 nanofarad capacitor, what was the initial design. And you see with this higher capacitance value here for the C3 and the aluminum electrolytic capacitor, I finally got also under the limit. So with this aluminum capacitor for the, let me say, good stability, and the higher input capacitor for the IC, I get a quite good result for the conducted emission. And here, compared to the 100 nanofarad capacitor, this was the measurement before I showed before. I scratched the limit, and also here in higher frequency, there is here it goes up. So this is, yeah, we can finally pass the conducted emission test with the aluminum capacitor. So before we are going to the second design, we will have short a look about the output capacitor, because they are also important for the stability. First, we go from right to left. So this is C7. It's a ceramic capacitor, 4.7 microfarad. It's there for filter the output noise. So when we had a look at the impedance curve, 3 megahertz as a self-resonance frequency, DC bias with at 5 volt is not quite high. So this is a good choice for suppress the output noise. Then for the C11, it's a ceramic capacitor for suppress the switch noise. Here again, I increase the capacitance value to have, it's maybe marginal, but it's a better performance electrical point of view. And with the DC bias, I shifted to the right point what I want to have it with 1 megahertz. So this was my approach to get here better performance. And also for the bulk capacitors, so for transient loads, like we have here the C2, also marked here in the design. Of course, 1 millifarad is quite high, and it has also been charged to it. But compared to the performance, so this is a polymer capacitor here, the output. The ESR really goes down to 8 milliohm, and also impedance is quite low. So this is a good choice to have also to buffer the energy when there are transients until the control loop can take over and is stable again. Then also the control loops for the old design, or also for the design with filters. So when you think about current loops, they are here. It was not the really best solution of it. So in the other design, we really think about or thought about it, and we really keep it really small. And here it was quite big, and therefore we had also this radiation. So second approach, so new design. So here was the picture. So here you see the picture of the real prototype. We placed, or we used everything what we had as what we thought before. So yeah, we have more filter possibilities also. So we had also we have the possibility to place an coma mode choke. We monitor the output voltage. We choose the capacitors regards to what I said before, and also the output capacitors are placed as I discussed before. From the design, from the design, it looks now like this. So this is with couple pores, and here you see the general overview. So it's really more compact, and of course more wires, and also here wires fence. Closer look to the current loops. So we keep it short. So really, we are now on the right corner. What I show now is, here are we in the design. So we have really, short and close current loops. So this will help us for the radiation. Here on the right side, you see it how it is in the design. Also the ground connections from the filter products or the filter components, and the connectors are now here placed with wires. So there's good connections to the ground. This is important to have a good performance. This was also done by here. Then the measurement of the second approach. So with input filter, but still without a common mode choke. This was an option what we have here. Conducted emission. So we are under the limit. Everything's good. Here we have some increase, but we have to check where it comes from. And also from radiated emission point of view, we have some buffer to the limit. So yes, we achieve our goal that we pass the EMC test. But what we can do to have a more distance to the limits. So first we can try to, or we insert some chip bead ferrites instead of the common mode choke. So we use the pads to place some chip bead ferrites. So you see, we choose the chip bead ferrites accordingly to the switching frequency. So we really suppress the switching frequency, but still in the higher frequency there, it's not an issue because we have a lot buffer, but it's still there. But what we see also is that there is an the suppression or the noise from the horizontal and the vertical measurement is quite different. So maybe this will lead to to other issues from the design. But of course, for EMC test, also here is everything fine. We are quite far away from the limits. Of course, we then use, or we placed the common mode choke. So now the measurement what I show here is with the common mode choke. It's an SL2, so of course it was chosen accordingly according the switching frequency. And we see, okay, the suppression from the fundamental is not as high as we see it before from the chip bead ferrites, but also when we have a look at a higher switching frequencies, they suppress it quite broadband. So it's really a good option to think about it, to place in the design, to have a really good suppression. And especially when we have a look at a radiated emission with the common mode choke. So now horizontal and vertical radiation is suppressed. It's more or less the same values we have here. So it's really a good filter solution, and we have enough buffer to the limits here. In the end, for my conclusion, so the EMI compliance is no black art or black magic in the end. When you understand the purpose of each part in the schematic, and when you understand your schematic, so please select the components what fits best for your purpose. Beware of possible parasitic effects. You can simulate it. You can have your prototypes. You can also simulate EMI and so on. So please think about interaction of components and how they behave in your design, and of course create the layout with thoughts or considerations. As you see from the first design to the second design, the the size keeps the same and the placement of the components, also where it placed, but how the components are placed and also the tracer designed is in a different way, and this leads to an better EMI result. And of course, what helps very often is to ask a colleague with experience or who also did some or have some the same issues. You can ask also an expert, so an external consultant and so on. And of course, you can ask us to support you for components design and so on. So we are here to support you. Yeah, so thanks for your participation. Hopefully you get some insights. And now I'm here for your question. I think we have still some time to answer a few or most of them.
Thank you very much, Frank, for this interesting presentation. Like you already said, we would like to draw our attention now to the questions. We still have, unfortunately, only 5 minutes left, but we're having some questions already coming in. And I would already start with the first question so we can get some of them done. If we are not able to answer all the questions now, we will answer them via email, like I said in the beginning. So don't worry, you will all get answers to your questions. So the first question is about something that you showed on slide 10. There you showed parameter for equivalent circuits. And the question is, where do I get these values? Maybe you can, just go back to that slide.
Yes, just a second. So slide 10. Yeah, so this is good. Also, you can get this parameter from our online tool. So from Red Expert, you can really move sliders to your voltage, frequency, and so on to get the values here, especially or like the ESR. For ESL, it's not shown in the Red Expert, but you can calculate it based on the impedance. And also, the second thing is where you can get the parameter is from LT-Spice. So our products are in the LT-Spice, and there you can also get the ESL value.
Thank you very much. So we'll switch already to the next question. What LISN did you use to measure the conducted emissions up to 1 gigahertz?
So it was, so we measured, as I said, here it was. So it was this setup, what we have here with this, it was an Rodian Schwarz listen, and then we have an EMI, also the measurement receiver, the EMI receiver, like from Rodian Schwarz, we then increase the frequency range, and we use this setup to measure the conducted emission.
Thanks for that. One question that we had coming in a few times was about the availability of our components.
Okay, so about how you can get it and when you can get it. Yeah, this is a good thing or a good question, because at the moment with that you don't get really the raw materials, so this is quite critical to get the material to produce the parts. And also at this current situation with the corona in China, also with the border Hong Kong and China, and also lockdowns because of the zero COVID strategy, it's quite hard to get the parts. Of course, we have the parts in our warehouse, quite good amount, but it's it's every time worth to talk with us and to make forecast and so on, that we have the parts ready when you need it. This is a good thing to do.
Thank you. So I think we can still look at one question. It's about the design one that you showed. Was it single-sided or a single layer?
So it was components were on top side, but I had as it was two-sided, so have top and bottom, and the ground was also on top side and bottom side.
Okay, let's just take just one more last. On the slide 39, 49, 41, what was the name of the ferrite beads?
So I knew that this question maybe come up. So it was like, okay, I don't have the article number here, but I can send it in advance. So this was what I show here. This was the performance curve of the ferrite. So with 1 megahertz, I have this 100 ohm here, or more or less 100 ohm here, and also for higher frequency. But please keep in mind that when there's some current flowing, so it starts to saturate and attenuation goes down.
Thanks for that. So I see that we still have questions left. Unfortunately, as I said, we are running out of time, but we will answer all your questions. We try to do that promptly. Yeah, now we are finished with our presentation. Like I said, if there are any questions left, we will answer them. If you have still any questions that you didn't ask in the within the chat function, you can email us. I will just show you something for the next presentation that we have. So yeah, this is our next presentation that we will have in nearly 15 minutes. It's about mesh and data made accessible thanks Bluetooth and mobile apps. Something different, but interesting as well. Frank, I want to say thank you very much for your presentation, and
Welcome.
we hope to see you as our attendees in the next presentation again. Have a nice day. Bye.
Bye-bye.